Hello, welcome to the second episode in our series of Tonearm Design Deep Dives. Today we're looking at bearings, which means we're going to look at different types of pivots, friction, and freedom of movement. Hello, welcome to the channel. I'm David Baker of Origin Live. This is my dad, Mark, who is our company founder. We've been making Tonearms for 30 plus years. The other thing not many people know is that we've been modifying turntables for even longer than that, around 40 years. During that time, you've looked at tons of different tonearm designs, bearing designs. You've had the opportunity to get up close and personal with them. That's definitely informed the way that you have designed our tonearms. But I guess also I wanted to know, having had all of that experience, what would the ideal tonearm bearing do?
Yeah, well, that's a great question because there are so many different types of bearing on the market, and you can go. I've been in this game for a long time, and I learned so much just because we used to rewire tonearms. We saw virtually all the tonearms on the market.
Wow!
So we've had a huge, exposure to all the different ways of
We've got quite a few, lying around actually.
Yeah.
Okay.
So just to run through the list very quickly of all the different types there are, you've got the conventional gimbal bearings, which are basically common roller bearings, type used in skateboards and so on. You've then got Uni-pivot bearings, which is a single spike in a cup. Okay, they have multiple variants of that idea, which we'll go into later. You then got dual pivot bearings, which is what we use. We use both gimbal and dual pivot being the better in our view most of the time, depending. And then you've got some very exotic ideas. You go into air bearings, magnetic bearings, hanging on a thread bearings, which is a kind of upside down variant of the Uni-pivot. You've got hinge bearings, which are like a bit of paper which kind of flex backwards and forwards. Vertair use those. You've got wheel bearings, which if you're, say, using a linear tracking arm, people can have wheels to run on the track. Okay. So there's an almost endless variety of different bearings. And it's really important to know what is the bearing trying to achieve.
Yeah, absolutely.
What does it need to achieve? And the most obvious one is low friction, because obviously if your arm is tracking a record and it can't move freely, some records are they're off center. So the track is not actually kind of going in a perfectly stationary position. It's moving in and out all the time. Yeah. Now, if your tonearm can't follow that because it's got a high level of friction, you're going to get a lot of sidewall force on your records. So that's going to cause increased wear.
Because the cartridge is wanting to go over here, but the arm, if the arm isn't following, that's a big issue.
Exactly, okay. So that's a big no-no. Low friction is the #1 requirement. And also, if you've got an arm which not only has to go like this, of course, to move across the record, but it's also following a groove, which is doing that. Sometimes you have a slight warpage. Almost all records have a slight warpage, but apart from that, if it's kind of just got to move and follow the track up and down, if it's got high friction, it doesn't drop down nicely. It just stays up, and that's where you get mistracking. I mean, we know that from bearings. We get people sometimes saying, "Oh, my arm's mistracking." And so bearings are the usual cause for that. So low friction is the #1 requirement. The next one is probably rigidity in the bearing. Okay. Because although you want perfect freedom of movement, what you don't want is the bearing to be able to move backwards and forwards.
Yeah, of course.
And if you've got, say, I mean, we're talking about microscopic scale, almost inconceivably small movement, which does affect the end sound because it's amplified 8,000 times.
Because it's measuring something so microscopic as well.
Yeah, and it can create timing issues. So if your bearing is a little bit loose, you can get backwards and forwards movement because the arm is constantly under like a tugging motion, like a pneumatic hammer in reverse, if you can imagine that. That's the kind of impact of the undulations. It's introducing constant kind of shock waves into the tone arm. So movement is a very bad idea in a bearing, and we try and make things as rigid as possible. The next one is energy transfer, because you want to kind of dump energy out of the tone arm as fast as possible.
Yeah, because I think in our tube video in episode 1, we were talking about how we want stuff to go down the arm tube and out of the arm.
Yeah.
And not back.
Yeah, not only do you want to dump energy out of the tone arm, but you also want to stop energy from the turntable getting into the tone arm, because obviously all vibration that's entering the arm can travel along and affect your cartridge.
Yeah.
But that's which is more important, getting energy out of the arm or stopping energy getting into the arm? And ideally, you'd want some kind of joint or mechanism which would allow energy to get out of the arm, but not allow it to get into the arm. Mm-hmm. And I know some people will say, oh, that's impossible. But the fact is that bearings do favour one direction or the other, depending on the type of bearing. And it also depends a little bit as to which is more important. Unlike if you've got a very poor turntable and it's not isolating the arm board very nicely, then you probably want to stop energy getting into the arm. So it does depend a little bit on the turntable and the tone arm concern, the bearing design. So lastly, reliability, and we've got a good tone arm will last for 50 years plus.
Yeah, absolutely. I'm still using one of your original designs at home. It's performing great.
Yeah.
That's at least 30 years old.
Yeah. Where you get unreliability creeping in is if the quality of the bearings isn't that great, or they've been badly torqued up. In other words, they've been badly fitted, so that they start to misalign over a period of time.
Okay, so the bearing is very important and it has a lot to get right. You were going into some of the common and uncommon examples earlier. Could we go a bit further into them? What is a gimbal? What is a uni-pivot? What is a dual pivot?
Yeah. We started off with gimbals because that's what the rest of the industry was using, and so why reinvent the wheel, so to speak.
Okay.
But within roller bearings, there are an enormous number of variations, and it gets very tedious, to be honest. Development is really tedious sometimes. You've got so many different factors when it comes to the ball bearings, and they all sound different. You've got small ball bearings, larger ball bearings. You've got different types of steel. So you've got stainless steel, hardened steel, ceramic. You've got plastic ball bearings intercoat with that. You've got different types of race. That's all the cages which hold the cages which hold all the ball bearings in place. They all add friction. So, and also then you've got the smoothness of the actual groove which the balls run in. So we've experimented with ABEC 9, ABEC 7, which is the kind of tolerances on all these bearings. And on it goes. I'm not going to kind of bore you with all the details, but we have learned an awful lot, and we have to specify our own bearings now because we know what really does work best.
And I think one of the really interesting things to me about the gimbal is also where you decide to put it really matters. Because obviously with the first, your first product in the tone arm domain was a modified Riga. And Riga have their ball bearings inside of the arm tube, which is a bit of a problem if we consider how important the arm tube is. And you took them outside of the arm tube, and they're in a kind of their own housing, so to speak.
Yes, they are inside the tube, and that is a huge issue because they do vibrate significantly. And what we found was that when we started modifying Riga arms, we used to bore out the yoke, which is the outer part that holds the tube. And we'd put the bearings inside the yoke. And that made a big difference.
And why did that make a difference, having them outside of the arm tube as opposed to in direct contact?
Well, it reduces the vibration in the actual arm tube.
Yeah, so rather than vibration happening in the tube, it's external.
Yeah.
Okay, interesting. So, I mean, more pivots, maybe we should go into something like the Uni-pivot.
Yeah, I mean, you could start with the Uni-pivot because that's the simplest of all bearings. For those who don't know what a Uni-pivot is, I'll just draw one quickly on the board. So you've got your tone arm. I'm going to draw this very roughly just so the principle comes through. And you've got a spike and a cup which is mounted onto your arm board. Okay, so that's your turntable down here, ground zero. And the arm is free to both rotate and move up and down. It's a beautifully simple bearing.
A lot of freedom of movement there as well.
Incredibly cheap to make. So that's why it is favoured by most of the budget tone arm manufacturers. The disadvantages are that the spike is vulnerable. Those spikes can chip, and we used to have name arrows in particular coming in, and they'd have I think they used to use a ruby tipped point, I could be wrong there, but they would shatter if they were badly handled, and that would cause real issues. The freedom of movement would just completely disappear.
Yeah. This to me looks a little bit unstable. Is there a worry with Uni-pivot about kind of azimuth stability in the way that the arm is going to track?
Very much so. I mean, what they do to get rid of this problem is they suspend their counterweight very low down. So your counterweight would be, I'm going to just draw this. Counterweight can be all sorts of shapes, but just drawing a simple one. Being so low, that counterweight automatically tends to stop it wanting to just fall over, because it would just fall over if there's no counterweight hanging long way below. The centre of pivot is obviously here. Yeah. Okay, so there are multiple variants of this particular design, and one of the best is that if that's your spike, you've got 3 ball bearings that the tip of the spike locates into. Okay, and those are very nicely, tightly housed in the base, so to speak. But you've still got complete freedom of movement here. But the beauty of this is that it's very rigid. In other words, if the spike wants to move that way, it can't. Whereas in the cup, it's very rarely a very sharp pimple at the bottom. You've got a lot of flat area, so the spike can move microscopically in the bottom of the cup. Okay, so this design avoids that. The problem is it increases friction quite dramatically because
there's more contact area.
Yeah, exactly. There's much more contact area. That is possibly a good thing in terms of getting vibration out of the arm, which is the reason it works.
It helps with transmission.
Yeah. So this has been found to work, even though theoretically you might think, oh no, there's too much friction there. It's all a balancing act as to whether you want rigidity outweighs the reduction you get in friction. Quite an ingenious variant of the Uni-pivot, which has also arrived recently on the SuperTrack arms, because up till the SuperTrack arrival, I thought that we'd seen everything there was to see.
I think a lot of people had thought that,
No, but it's a very cunning design, and basically, if that's your arm tube, it's got a face coming, a kind of rigid face. It's all rigidly attached to the arm tube, and that has a spike. I can't remember if the spike is on here or whatever, but the arm is restrained by a hanging thread. You've got a little V-shaped thread which which creates stability in the azimuth direction. But the advantage of this design is that when the arm is tugging like this, there's no give at all. The spike is...
Right, so what you were talking about here, where there's potential for it to shift forwards.
Yeah.
Because it has this, I'm trying to remember how, Richard has a great acronym. SuperTrack is an acronym, but I'm forgetting what it stands for now. But it cannot move forwards.
That's right, yeah. It just can't move forwards.
Okay, so we've done gimbal, we've done Uni-pivot. We use the dual pivot. What's that?
Okay, the dual pivot is really kind of a variant of the Uni-pivot.
Okay.
It's just the idea taken to another level, really. And so instead of having one Uni-pivot, you've actually got 2 points going into a couple of cups. Mm-hmm. This is all held on what we call a turret plate, because the turret rotates.
That's in our higher end arms.
Yeah,
and in our lower end, it's held in the yoke.
Yeah. So if the yoke is rigidly attached to the arm itself. So your up vertical movement, in other words, the arm going up and down, is taken up by the dual pivots, mm-hmm. and the rotation is taken up by a conventional pair of gimbals, which are simply attached to this plate here. So you've got your bearings like so. One thing I forgot to mention about Uni-pivots, though, is that a lot of people do not like Uni-pivots for the simple reason they are incredibly fiddly to set up. Mm-hmm. You have to get them to balance perfectly in the azimuth, and that can be a bit of a tedious setup. Whereas dual pivot behaves exactly like a conventional gimbal arm. There's no worry about azimuth. It's always it's set up at factory. I mean, we use this as a setup jig, so everything's perfectly aligned at the azimuth and the Tonearm base.
And also one of the advantages of the way we do it is that you can actually adjust azimuth if you want to, which isn't necessarily available with gimbal bearings.
Yeah.
One of the things I am interested in is we use a mixture here. So we use gimbals down here, and we use the dual Uni-pivots or dual pivots. Is this a compromise? Because if we're thinking that straight pivots are better than gimbal bearings, why would we use both?
Okay, so very good question. Why do we use a hybrid design? And I suppose the simple answer is that these bearings do different things. And I wouldn't say that there's one which is necessarily superior to the other. It depends on how they're done. As we went into earlier, a very good ball bearing can compete with a Uni-pivot. A poor ball bearing won't compete with a good Uni-pivot. And a poor Uni-pivot won't compete with a good ball bearing.
Right,
so
okay.
It really is a question of how well it's executed.
Right.
And each of these bearings has different pros and cons. The advantage of the gimbal bearings is that they transmit energy out of the arm better. And that's what we're trying to achieve up to this point. So it's a balancing act. One thing that's probably worth mentioning is that the dual pivot idea probably came into being about 10 years ago. And
no, a lot more than that for sure.
Yeah, probably is, maybe 15. But it's interesting that 4 different manufacturers, one in Australia, one in Germany, one in the States, and one in the UK, all came up with the idea simultaneously. No one copied each other. I mean, I didn't copy anyone when I came up with this idea. But we all arrived at this conclusion at the same time. And they do things very slightly, there's different versions of this. Like some people will go for a near Uni-pivot. In other words, most of the weight will be on one of the pivots, and then they'll just offset the center of gravity slightly and have a little outrigger here, which will just take a little bit of the weight and
Okay.
create enough stability so that it acts like a gimbal, and you don't have this ghastly kind of rocking motion, and the thing looks as if it's at sea when you landed
Yeah.
on the record.
So it's kind of like a modified uni-pivot into dual pivot kind of
Yeah,
assembly. Okay.
yeah. That's the variant, and then we can move on to other types of very exotic bearings. One thing which was all the rage for a while and was the bee's knees in the hi-fi world was something which floated on a bed of ceramic fluid.
Okay.
So you had this little kind of, I mean, we actually had one of these arms. It was the Vivid arm, I think, and we actually tested it and listened to it. So it had magnetic fluid, a bed of magnetic fluid in here, and on that floated the actual arm itself, and it didn't capsize. It had a, you know, a large
It was
enough.
seaworthy.
Yeah, exactly. Yeah. So the arm sat around here, and the idea of this was it decouples the base, well, the arm from the arm board,
Right.
because you've got a.
So environmental vibration, structure-borne vibration.
Yeah, and it in the, you know, it rocks and it rotates, so it works very nicely as far as low friction is concerned. Yeah. So going back to this, I had to kind of, I have to confess, I was very slightly amused by the idea that it would decouple the arm from vibration, because if you've ever seen, well, films of battleships or getting blown up by undersea mines.
Which you have, since you're a naval engineer.
Yeah.
Okay.
But if a battleship or any ship goes over a mine, the mine makes no contact with it. It just, if your mine goes off in the bottom of the sea here, the shock wave through the water breaks the ship in half. It's absolutely, you know, and a lot of these things like magnetic bearings and string bearings suffer the same problem. They all transmit vibration.
Right.
Everything transmits vibration. Even a magnetic field transmits vibration. Air bearings still transmit vibration. So to a lesser or a greater extent. So I just never forget that, really.
So everything is going to transmit vibration. It's about trying to find the best compromise.
Exactly.
Right. Okay.
Exactly. Yeah.
Okay.
Yeah.
Hi, I'm quickly interrupting this video just to ask that if you're finding it worthwhile, please could you hit the like button, subscribe to the channel, and also press the bell notification. It really helps us to carry on making these videos. And what we want to do is carry on having open conversations about vinyl replay, and also giving you insights into how we've been making turntables and tone arms in-house in the UK since 1986. Well, not me personally, because I'm 31, and that's... Anyway, you get the idea. So, thanks, and back to the video. Okay, so, more bearings.
Yeah. The list goes on.
Let's go.
The next one is the hanging thread. And I could be wrong, but I think the Schroeder arm was the first to actually use this method. And it's a very good, I like this method, it's very ingenious. So you've got a thread which suspends the tone arm, okay? Center of gravity is nice and low, because if you think the counterweight is also around here, it's hanging. What Schroeder also does is it has some form of paddle, I think, that means that it's also damped a bit, because they put the paddle into a ferrofluid of some description. This is not an uncommon idea, and whether it's Schroeder or well-tempered that do this, I can't remember. So that's an ingenious method, because it's got complete freedom of movement. It can rotate freely, and it can also pivot freely. It's like a uni-pivot at this point here, which is wonderful. I mean, you know, it's a great idea. Yeah, there is another good little variation of this arm, because this method rather, is because it's so inexpensive. It's you know, I think Schroeder used a Kevlar high strength thread here, so they maximizing the rigidity that they can. But what you can also do to kind of stop the thing swaying and becoming uncontrollable, because that is the problem with this arm. If you can imagine an arm that on a thread, it's got to be, you know, controlled, because you've got to cue the record without the thing going all over the place. What Clear Audio do is they put a magnet down here. Okay, so this is a magnet, and you've got a little bit of metal in the arm here, which means that it's strongly attracted there, and you don't lose too much movement, you know, freedom of movement. It's not a big introduction of friction, but it does stop the arm kind of going or wandering all over. The next kind of variant of this is the magnetic bearing, which is more difficult, and I can't remember the exact details of this, but basically you magnetize the arm. I think they hold it top and bottom, all right, between two magnets, and that gives the arm freedom of movement, but it's contacting absolutely nothing. The arm cable is the only thing which gives it any friction, and as I missed out mentioning, in our gimbal arms, there is more friction in the arm cable than in the bearings themselves. So the arm cable is about 70% of the friction on a good bearing. Right. So you still got a fair amount of friction even with a magnetic bearing, because that arm cable can feed in vibration.
And this is maybe an interesting point to go to. So is that the reason that you'll see some arms like maybe something like the VPI, where the arm cable isn't going through the base, it's coming out the top? So is that to do with reducing friction?
VPI are an interesting point. They actually use the arm cable to set the side bias.
Right.
Because it takes, I haven't tried it myself, but I can imagine that you would be fiddling around for a little while to get this just right.
A certain amount of cable twist or something like that.
Yeah, and the way it's bent. So there is friction there, but they're using it to create side bias, which in some ways is a good idea, because side bias in itself can introduce quite a lot of friction into an arm and vibration. We've always found that an arm sounds better with no side bias at all. I think you need to put it on really to reduce record wear and to maintain a very central image as well.
I disagree with that, and we can have two different preferences on this. I think it sounds better with it on in terms of focus, and also sometimes you can get a little bit more detail with it on, is what I find.
Yeah, and I understand that perfectly, and I get it. It depends what in the music you're listening to, because it is swings and roundabouts, and I think depending on your musical preference, whether it's a roundabout or a swing, you know, is what you'll come down on.
Yeah, and that's definitely the thing, is preferences will, if you're leaning towards one area of the music, you might prefer a certain setting. And the other way around, and that's often what leads designers in all sorts of directions anyway. Is there, just staying on cables for one last question, is there a reason that you would want the cable to go through your bearings rather than being on the outside, rather than being external and having no friction, no cable twist, that kind of thing?
Okay, that's an excellent question. One explanation is that you get much better shielding if the cable is protected by the bearings. I have had instances where I've been doing test cables and where I've run the cable outside of the tube, and I only need 4 inches of unshielded cable wire to get a radio signal coming through sometimes, because the signal is magnified up so much that it even very faint radio signals don't need a lot of amplification.
Can you shield an external cable particularly well, or is that always going to be a bit of an issue?
It will be an issue for if you're close to a strong radio signal.
Right.
Okay.
Interesting.
But the other reason is to reduce friction, because if your cable is slightly off center from where your pivot point is, if your pivot point is here, if your cable is, say, wanders off here, all right, you've got a lot of extra leverage that's going on.
Right.
And it does restrain the movement. You would have thought, when it comes to rotation in particular, I mean, in vertical movement like that, doesn't make too much difference. But in terms of the rotation, if you can imagine that wire is then scraping along the outside of your hole, and it is disastrous. So we restrict our hole to 2 millimeters, and I found if you even put a 3 millimeter hole in, it increases your friction.
There are compromises whether it's outside or inside your bearings.
Oh, absolutely, yeah.
Okay.
Okay, so we're ready to move on to the next
There's
bearing.
another one. Oh my goodness. Okay.
Okay, so to just talk about air bearings now. I haven't seen air bearings used on a gimbal bearing or a uni-pivot, but they are used very consistently on linear tracking arms.
Right.
So for those not familiar with linear tracking arms, you've got a track which is rigidly attached to your turntable with a pillar usually, and then there's a sliding mechanism.
If we get a record
If this is your tone arm, all right, that's your cartridge on the end. This is your counterweight. So to reduce the friction of this arm moving across, you have to use a very, very low friction bearing. So air is the favoured way of doing it. There are lots of issues with linear tracking arms, because the big advantage is that it's always absolutely parallel to the groove.
Right.
At right angles to the groove. So there's no tracking error.
Yeah.
And I don't want to talk about tracking error at the moment, but it's a huge advantage to be able to not have any tracking error.
Okay.
But you've got a known problem with these arms, is that they are incredibly high inertia, because instead of the mass being kind of just the tube, you've got to move the whole tube and the counterweight and the yoke sideways.
Right.
So the only thing that's going to, there's variants of this. I mean, some people have tried to get servos which drive this along perfectly across the record, but the trouble is that record grooves vary slightly, and most people don't end up using servos.
Is that more of a 80s kind of design? Am I right? Like the Bayogram or some of the older ones?
Yeah, I think that within that servo idea, you had a certain amount of flexibility within here, so it would compensate if it got kind of out of sync.
Okay.
It's not a bad idea that you could have a kind of pivoting arm like that, which would give you a kind of minimal tracking error, but at the same time not kind of have the huge issues of
new design coming soon.
Inaccuracies. Yeah.
Okay.
Yeah, but so there are some very well-known brands, and the effective mass of this arm is running at 70 grams. I won't say which arms they are, but that is, to me, is too high.
Right.
Because we were talking about friction before, causing sidewall wear in your vinyl groove. Well, none of the reviewers that reviewed these very heavy effective mass arms commentate on this, and who knows? I mean, who's going to sit down and play a record 2,000 times and find that it's
compare
worn.
It to an original?
Yeah, and find that it's, well, you have to do, one with a uni-pivot or conventional arm, and one with a parallel tracker at 70 grams.
And in our next video, we will be.
Yeah. So you've got
you're
to move.
concerned about it causing wear to the record?
Even if you've got frictionless movement here, that mass is so high.
Yeah, it's the whole of the
you're going to cause. I mean, it's like if this way, to take it to the extreme. If say this arm weighed a ton, all right, and it could move friction free on here, you can imagine this poor record groove trying to move a ton weight. All right, it's not going to do it.
Right.
So you're going to get record wear on the groove. Now, whether that is a serious problem or not, I wouldn't be prepared to say. But from a reliability angle, I would avoid it personally.
Yeah.
As a designer, I just wouldn't go there.
And we've had some in the past, and we decided not to pursue it.
Yeah, we have. They were not in this order of things, though.
Okay.
They were very light, and you can design linear trackers with what I describe as a reasonable effective mass, say like 25 grams.
Okay.
It is achievable. Well, you could even go up to 30 grams probably, but there are so many other hiccups which you've got to overcome with linear tracking. I mean, the first thing is you've got to have an air pump, and some of them are, well, they're usually quiet in all honesty, but I have heard instances in the past where they're so noisy you've had to put them in the next room. So the air pump, and then you've got the reliability issue coming in, because eventually airlines, air pumps, they all can fail. So
maybe the more fundamental thing that I've always wondered about these is just the sheer amount of parts needed to execute a linear tracker.
Yeah.
And then when we're talking about trying to reduce vibration, every added part can be another part that helps to reduce it or helps to increase it.
Yeah.
So there are some designs I've seen that, I'm kind of like, I don't think I'd ever want to put this on a record, and that's probably very judgmental of me, and I should, the proof is always in the pudding. Listening will always tell the story, but it puts me off.
Yeah, they do look awkward, some of them. And to be fair, I have to confess, I played around with, I did design an entire linear tracking arm, but never built it.
Yeah, I remember this. I remember.
In the end, I abandoned the idea because mine worked on rollerblades, so incredibly low contact area, very low friction,
very groovy,
and it was very light, and it ticked all the boxes. But a tangential tracker is a better idea, and we're looking at tangential trackers now for our very high-end arms.
Okay. So that was air bearings. Are there any more?
Yes, I can think of 3 more. Okay. So we'll go through them very quickly. The first is a very easy budget bearing, which I played around with for a while and just could not get it to work. Well, it worked fine, but it just sounded terrible.
Okay.
But it is used on budget arms. So if this is looking head on at the arm, if this is your tube, you've basically got 2 spikes coming out of the side. Probably not drawing this particularly well. Okay, and they sit into 2 cups. I'm going to exaggerate the size of the cup like so. And the idea here is that you've got a point contact resting on a cup, and this is of course inside the yoke, and it can pivot quite happily. This yoke is then obviously just attached to conventional gimbal bearings on a vertical axle. The problem is that basically to get that cup into position, you have to put so much pressure on it that it feeds vibration through like crazy. And if you want these needles just to rest gently in the cup, there's still a lot of sideways pressure on them, because unless you're going to fracture your tips, because if you make your point very sharp, you end up fracturing it. So in large detail, what you end up with is something which is sort of fairly rounded there relatively. And although it's inside a cup, you've got quite a lot of contact area here. So it's a poor way of doing things. And it's the downward pressure is...
Yeah, I was just thinking, is there also more force kind of around here on the underside of those points than there might be if it was a kind of a uni-pivot or a dual pivot?
There is. That's the problem. When you've got a vertical point, it rests bang on the point nicely.
Right.
Where it's resting on its side, you always end up with a larger contact area.
Right.
It just seems unavoidable.
To actually keep it up in the first place.
Yeah. So the next one is invented many, many years ago by, I think SME may have invented it, but it was probably invented before then, but they just used it. It's what's called a knife bearing. To my knowledge, nobody uses this anymore because it is a terrible bearing.
Oh, really? Okay.
And basically it works on, if I can just draw it in 3 dimensions, instead of a point, you've got what they call a knife edge, and this is attached to your Tonearm, right? It doesn't matter how it's attached, but it is attached. And that rests in a V groove, all right? And that's restrained in all the various planes. I won't go into it in great detail. The problem with this is that it's got massive contact area. So although it works beautifully and it'll last forever, it's just not a good bearing.
In terms of that's going to feed vibration back into the tube, back into the structure. Okay.
Yeah, it's high friction. It just doesn't tick many boxes, basically, apart from reliability.
Right.
It's a super reliable. Yeah, it's a super reliable bearing.
Okay.
And then lastly, the flex bearing, which is a very interesting bearing because it tackles one of the problems with most of the other bearings. In fact, you could argue all of the other bearings, which is the problem of stiction. And stiction is that initial friction you get to start something moving. So if you have an object, like say my pen, and it's resting on the board, to get the friction to get that thing, rather the force to get that thing moving, because of the stiction, the force to get it moving is higher than the force once it is moving, okay?
Because of the resistance of the contact area between those two
yeah,
things.
Before it gets moving, there's a higher friction level, higher force needed. So if the bearing is stationary, then, in other words, the arm is not moving. To get it moving demands a little bit of force on the ball bearings. It's very, very minute, but it's there. So it's an arguable advantage to get rid of that. So the bearing which avoids stiction is called a flex bearing, and they come in many forms, flex bearings. The simplest one is simply a very thin wafer of material, and it can flex. It doesn't really matter how this is applied.
No, there we go.
Okay. But if you've got a rigid, say you attach this rigidly to your turret plate or the base of the arm, you can, and this is not a technical drawing, so please, it's just to convey the idea. This thin membrane can move backwards and forwards. Okay, it can simply bend, so it bends like so. And as you can imagine,
be moving the arm.
Yeah, so
like that.
Yeah, if you attach an arm to your flexible membrane here, then it's free to move up and down. Okay, because when it wants to go down, the whole thing simply bends down.
Right.
Sorry, the pen isn't working particularly well at the moment.
So it's not having to get a gimbal ball bearing. It's not having to get the racing, the balls to move.
No, that's right.
Is that also an issue for something like a uni-pivot, where a uni-pivot's trying to move? Are you still suffering stiction?
You're still suffering stiction because the point is like a tiny ball bearing, really, and that still has to move across the cup.
Yeah, so it's still moving microscopically, or, in the microns.
It's still having to scrape, so to speak.
Right.
But this avoids that problem.
Okay, interesting.
I mean, my argument would be that it's not particularly rigid. That is probably very controversial, but I'd suggest it's probably not quite as rigid as certainly a point and cup.
Okay.
Because because it's so thin, you've got the ability to pass vibration through this quite happily in a minute level.
And also vice versa, it can travel both ways.
Yeah.
Because it's quite a straightforward connection as well, isn't it?
Yeah.
Okay.
But it is a very good, it's all
in
of
terms
these
of friction.
Yeah, all of these things have huge pros
Yeah,
and cons.
absolutely.
And it's the execution of the design that's the important thing. In other words, this could make a very good bearing, there's no question about that. And if it's done well carried out, you can probably get over most of the rigidity problems.
There's just a lot of things to also get right alongside every bearing we've discussed,
Yes,
isn't there?
yes, there is.
So, I mean, now we've got to the end of our bearing list. Are there any that you would avoid at all costs?
The horizontal points are, yeah, they are a disaster. Knife bearings are a disaster. I think that would be about it, really.
Okay.
Personally, I would avoid the ferrofluids. The problem is that when you get to very finicky setups, some people really, they don't want to get involved. And so Gimbal is the simplest. That is so user-friendly.
Yeah.
It is
definitely.
the most user-friendly of the lot. There's no fiddly setup and all that kind of thing, which you can get into with some of these other designs.
Yeah, for sure.
Okay.
Well, thank you very much for watching. Like I say, if we've missed out a bearing that you know all about, please let us know about it. We'd love to hear. Thank you to everyone who's been leaving comments and likes and subscribing. It really helps us to carry on making these videos. If you have any questions about how we do things or our products, please get in touch. You can call us, you can email us, and you can check out our website. It's all linked in the description. Thank you very much for watching, and whatever your system is, enjoy listening this week. Thanks.